Hello, my name's Andy Lapping and welcome to this repeat presentation of the INCOSE 2012 Tool Vendor Challenge. This presentation was originally given in front of a live audience at the INCOSE Symposium. No PowerPoint, no pre-recorded videos, just the tools themselves. So, let's get started. Let's start by taking a quick look at the brief itself, supplied by INCOSE before the event. The challenge revolved around improving the effectiveness of the firefighting capability of an imaginary country, Forestia. Forestia currently has local departmental operation centres, or DOCs, that own and manage their firefighting resources. However, this leads to problems in the sharing of those resources, and so the Ministry of Interior has asked for a Permanent Emergency Response Coordination Centre, or PERC, to be built. That control centre will take over the management and coordination of resources. And the Ministry would like a phased delivery with some level of capability, delivered before the end of the summer. If you want to review the requirements for the challenge, simply go to the INCOSE website for the 2012 Symposium and click on the Vendor Challenge link. Now, when we were doing some research for the challenge, a colleague sent me this report from the Jerusalem Post, his local newspaper. This recently released report detailed the findings of an inquiry into a fire that happened back in 2010. In particular, it highlighted the failings of the emergency services to effectively gather and analyse information and effectively coordinate their available resources. Now, we find that report incredibly relevant to the challenge, and it drove much of our response. Now, before we dive into the solution itself, let's briefly take a look at the tool set that we used in its creation. Our requirement set was held indoors and broken up into stakeholder requirements and system requirements, with traceability between them and back up to the original brief. Now, those requirements didn't evolve in a vacuum. They were developed in conjunction with modelling. In this case, a UPDM model in Rational Rhapsody. Now, traceability is key, and we implemented traceability between the different views in the model, but also back up to the requirements indoors. Doors Web Access and Rational Design Management gave us web access to the requirements and the model, allowing us to get feedback from reviewers and stakeholders without any need for the tooling or any need to wait. Our reviewers just opened a web browser and they were able to browse around the models and browse around the requirements and give us feedback, and we saw that feedback immediately. Rational Team Concert gave us project planning, along with task management and formal change management. And lastly, the Architectural Optimisation Workbench from the IBM Research Labs took our proposed system views and gave us back an optimised architecture. Look out for a further video on that. This is Rational Team Concert, which gave us project planning, task management and change management. Here we have a timeline for the project, broken down into 2 releases. Each release has a number of plans, and each plan has work items associated with it, assigned to teams. Rational Team Concert goes beyond month-to-month planning. It's a tool that can be used for daily work or even hour-to-hour planning. As a project manager, Rational Team Concert gives me live data. I don't have to send out requests for status updates and wait for them to come back. I can track the progress of my teams and their workload. If I find one of my team is overloaded, I can make dynamic changes to the plan simply by dragging and dropping work items. Rational Team Concert also gave us formal change management of the DOORS modules. If requirements needed to be changed, then those changes were logged and tracked against a formal change request raised in Rational Team Concert. Okay, let's see the solution, starting with DOORS Web Access, where we can browse around our requirements using a standard web browser. Here's the original INCOSE brief, imported so we can start adding attributes, such as whether an item in the document is a requirement or just a contextual information. The stakeholder requirements we developed are linked back up to this brief, and here we can see those links, and even see the detail of the linked items without changing our context through these rich hovers. Of course, we can select the linked requirement and dive into it. On the right, we can start discussion threads around a requirement and get instant feedback from our reviewers. Each object in DOORS has a URL, and that's a link that I could paste into an email to have a reviewer look at a specific requirement without the need to try and locate it. They just click a link and they're sent directly to the requirement I want them to review. If I click the link, I can open the item either in Doors Web Access or in the Rich client like this. We imported both the stakeholder requirements and system requirements into the Rhapsody model, along with any links made by the requirements engineers so they could be visualized inside the model. As a requirements engineer, I can find out how a requirement's been dealt with by navigating directly into the model, like this. As an architect, I can find out where a particular requirement came from by navigating out of the model, like this. This view shows that the system requirements are covered solely by the system views of the model, while the stakeholder requirements are covered by either system requirements or by operational views in the model. Now, as well as coverage analysis, I can get impact analysis. When a requirement changes, I can see all of the requirements or model elements impacted by that change. Back in the model, I can automatically generate table views of the imported requirements, as well as matrix views to visualize or even create traceability. Now let's look at the UPDM model, starting with this AV1, which gives an executive summary of the architecture and the views we use to model it. Now let's look at the more graphical views, starting with this OV1, a high-level operational graphic showing the concepts we're about to explore. Now it's important to understand that this is not the architecture, but the architecture we create will actually realize this concept. Moving on to the capability views, starting with this CV2, which shows our capability taxonomy. Now we started a little bit higher than the original forest fire capability that INCOSE requested. We've modelled an emergency response capability, which could then be earthquake, flood or fire, and fire could either be a fire in a city or a forest fire. Now of course the one we're going to focus on is that forest fire capability. Here's a CV4, which shows that our forest fire capability breaks down into 4 others. We're going to need a detection capability, an evaluation capability, some sort of planning, and some sort of response. And it also shows which other capabilities that these capabilities depend on. For example, communications, which might be secure between emergency services, or indeed unsecure. That might be a member of the public, for example, spotting a fire and calling it in. Now we can start exploring the behavior of our capability at a high level through this black box OV5 operational activity model. So we need to detect that there is a fire, and then we need to verify that it is in fact a threat worthy of our attention. We'll assess the situation, determine what resources we have available, allocate them appropriately, and then deploy them into the field. And then we have 4 things that are going to happen in parallel. We're going to evacuate the immediate area of the fire. We're going to evaluate where that fire could spread and evacuate that area. We're going to try and prevent the fire from spreading, and of course we're going to try and neutralize it. From this view, we can begin to explore the logical architecture through this OV2 operational resource flow description. Here we've abstracted up again. So we have 2 types of command and control, 1 central, that'll be our perk, and 11 local. In addition, we need some sort of fire detection system and of course responders. And here we can see information flow between these nodes, such as, for example, our detection system is going to send us not only the location of the fire, but the time at which it occurred. Our central command and control is going to send allocation orders to the responders, but also to the local command center so they know to expect them. And we're going to get situation reports back, both from the local command and control and also the responders on the ground. Now those information flows did not evolve in a vacuum. They came from the next diagram we're about to explore, namely this white box version of the OV5, where we can begin mapping our operational activities to the nodes that perform them. For example, the fire detection system is going to detect a fire, and then the centralized command and control is going to try and verify it. If they can't do that, then they'll request that the local command and control center confirm that threat for them. If it is indeed a threat, the central command and control is going to assess the situation centrally and then allocate resources out accordingly. The local resources will be told where to go, which DOC to attend, and the local command and control will give them their actual local deployment orders. Then we have all the parallel behavior there over on the right, and this feedback loop coming back up, so that our central command and control can reassess the situation and reallocate resources should they need to. Now this diagram is very interesting for us because we can actually execute it. Here, for example, we can start stepping through the diagram using the SysML token flow semantic, and we can really get a good handle on whether our description of the system at this point is actually correct. Next we have this CV6, which shows in a very neat way the mapping between those operational activities we just described and those capabilities that sit above them. Those were the operational views. Next we can move on to the system views, starting with this SV4, which is essentially the systems level version of the white box OV5 we saw previously. We can begin to explore which system functions we need, and from that derive an architecture. Now we had all sorts of weird and wonderful ideas, ranging from UAVs for flybys to cloud seeding, so this is just one possible system configuration. Here we decided we needed a satellite data center, which is going to feed us information about potential fires based on hotspot analysis. Our system will need to verify that by making an assessment of the satellite image, and if we can't do that in the central control center, we'll need to get verification from a DOC closer to the actual site of the fire. We're also going to get weather information from the weather center and use that in our assessment of the areas likely to be affected by the fire, how it's going to spread and so on. Based on the location of the fire or fires, we'll prioritize which areas need the most urgent attention. Then we'll assess and allocate our resources accordingly. There is a feedback loop from the resources on the ground feeding back situation reports to us so we can constantly reevaluate the situation. And on top of all of that, we're going to update the media and infrastructure on the current state of affairs. Now where the flows cross these swim lanes, that will start leading us to the necessary external interfaces, shown on this SV1, context and external communicating subsystems. For example, we have external interfaces to the weather center, to the satellite systems data center, and those are going over encrypted channels. While the communication from the public will be over unsecured lines, but then routed to us by the emergency services over encrypted channels. On the right-hand side, you can see all the communication channels to the aviation authorities, the DOCs, the media, and also the resources themselves, who can report status information back to us, as well as their own local DOCs. Then we can begin to fill in the PERC system with its internal systems, shown on this next SV1. Here we have a mixture of systems and human resources, the humans are shown in green. For example, we have subject matter experts, who will use specialist software to analyze the data we receive from the weather center. We also have our own UAV for doing flybys to confirm possible threats. We can show where commands and information are being passed, along with where control is being exercised. Now this is the final 1.0 version, deliverable next year. We have a version which maps to the 0.3 first release, which looks like this. Most notable on this version is the lack of any specialist software or any UAV system. From this view, we can generate this SV3, system-to-system matrix, which is a nice n-squared view of where data is being exchanged. And we can also generate this SV6 system resource flow matrix, which shows us a summary of the information flowing between the various systems and what lines that information is flowing on. And lastly, we have this SV5A, Operational Activity to System Function Matrix. This completes our traceability. Now we have traceability from the systems to the system functions they perform, to the operational activities that specified them, back up to those higher level capabilities that were required by the stakeholders. Now it was at this point that INCOSE changed their requirements and stated they would like a similar capability to deal with earthquakes, floods, and so on. So we took our solution and created this more abstract version by analyzing what the essential functions were. And this led us to a more generic disaster recovery architecture that could be used as a template for future work. For example, any disaster recovery system would need some specialist software and some SMEs to perform analysis. Well, that's about as far as we're going to go with the UPDM model. Look out for another video showing the final piece of our solution, where we take the system views from the UPDM model and feed them into the architectural optimization workbench, which creates an architecture that is optimized for the scenarios mentioned in the original INCOSE brief. For more information on any of the products you've seen here, go to www.ibm.com/rational/software. Or for more information on Rational Team Concert, go to jazz.net. That's it from me. Thank you for watching. See you next time.